The goal of this tutorial is to walk through a constant pressure process in PVT space. I strongly recommend that you review your lecture notes prior to watching these videos. There's a lot of new terminology associated with PVT space and its various projections that you could imagine getting a little lost in the jargon if you haven't already looked through that stuff. The three projections that we'll be considering, and really the only three projections that you can construct, are TV plots, PV plots, and PT plots. Two things to note. One is that the ordering of the variables tells you the orientation of the axes. They are generally quoted as being the vertical axis first, then the horizontal. So a TV plot has temperature on the vertical axis and specific volume on the horizontal. The second note is that these letters, L, V, S, those are telling you about the phase of the medium being described. So L is liquid, V is vapor, and S is solid. We won't do a whole lot with solids in this course, but the phase is listed nonetheless. In addition to these three plots, we're also going to consider the movement of a piston meant to represent the evolution of our system. So our system would be that blue material inside the piston cylinder, and we'll see what happens to it as we represent some evolution on this set of three plots. To begin, we need to locate our initial state. I'm going to say that the material inside the piston is entirely a liquid, and we'll put a point on each plot to represent where it sits. So on the TV plot, it's over there to the left of the vapor dome. On the PV plot, it's also there to the left of the vapor dome. And on the PT plot, it's sort of up in the middle. As we evolve our system, I'll also note the phase of the system. So right now the system is in the liquid phase exclusively. It's currently just one phase. It should go without saying that we're considering a simple compressible system. That will almost always be the case. We don't want this thing changing its chemical composition as we move the piston around or anything complicated like that. So now we'll start evolving the system. One thing I recommend is to pause and rewind this video as needed because we're simultaneously going to evolve the system on all three plots and move the piston around accordingly. It's a little too much information necessarily to see all at once the very first time through, so I highly recommend that you review these plots and their evolution a few times just to make sure everything makes sense. So let's start evolving the system. Okay, the piston is going to start to expand just barely, and on each plot you'll see a red line representing the trajectory to get to the next state, which we'll label F. Okay, so let's make sense of this. It was a constant pressure process, so the PT and PV plots have to have horizontal lines. You have to stay at fixed pressure. That means only horizontal motion on a PT or a PV plot. That part makes sense. The TV plot, you can see, does represent an increase in temperature as you increase the specific volume. The specific volume must be increasing because we were expanding the piston. Now you may barely have noticed that it even moved. Liquid is not compressible, meaning that generally speaking it's very difficult to change its density, which is what corresponds to a change in specific volume. If you remember, specific volume is the reciprocal of density. So you can push on it, you can pull on it, and it really doesn't change volume very much if it's entirely liquid. As we'll see in a minute, it'll become a little easier to move the piston once some of the liquid begins to transition into vapor. So as a result, while you're doing this, presumably the piston is experiencing some sort of external heating that I've not attempted to represent in this video in order to raise the temperature like that on the TV plot. That steep slope to the left of the vapor dome on the TV plot is very standard behavior for a constant pressure process. Okay, so our next step is going to be to cross the vapor dome to go to a new state G that's on the right side of the vapor dome instead of the left. As we do so, we're going to expand the piston. We know that we have to do that because, again, we're stepping forward in specific volume. And watch what happens to all three plots. So here we go. The first thing is that we start to have a two-phase liquid-vapor mixture. So immediately upon entering the vapor dome, some of the liquid is transitioning into vapor. When we reach the right side, we've reached a saturated vapor phase, meaning that right now it is entirely vapor. Let's walk through what happened in each plot. The PV plot is probably the easiest to understand. We just crossed the vapor dome with a horizontal line, as we had to since we were still operating at constant pressure. If you look at the TV plot, you can see that we crossed the vapor dome here with a horizontal line as well. That's much less obvious, so we know we have to operate at constant pressure. The TV plot tells us that while we're crossing the vapor dome, we're also operating at constant temperature as long as we're at constant pressure. This represents adding energy to the system that normally would have gone into increasing its temperature, but while you're under the vapor dome, that energy actually goes into freeing bonds that kept the substance as a liquid. So it's slowly becoming a vapor. All of that energy is going into creating a vapor from a liquid instead of raising the temperature of the system. That's why you operate at constant temperature. For a real-life example, consider heating water at its boiling point. You don't continue to elevate the temperature above liquid water at its boiling point. What happens is that you add more and more heat energy, the water becomes steam, and then once it's entirely steam, you can again start raising the temperature of the steam, but while it's transitioning from liquid to steam, you don't actually increase the temperature of the liquid. That's all that's going on in the TV plot. Finally, we want to understand the PT plot. Well, you'll notice that points F and G are in the same location. We didn't have any evolution on the PT plot while we were crossing the vapor dome and the other two. Actually, we can make sense of that. According to the fact that we're operating at constant pressure, we knew that we could only move horizontally on a PT plot. But the TV plot told us we're also at constant temperature. Constant pressure and constant temperature mean only one point on a PT plot. If that point hasn't moved around, we shouldn't see any evolution on the plot. Indeed, the left and right sides of the vapor dome and the other two plots correspond to a single point on the PT plot. Okay, time to evolve the system one step further. We're currently in a saturated vapor phase. Now we're going to continue heating the system so that we move entirely into a vapor phase. So we do that. The piston continues to expand, and eventually we'll reach a point S. S may seem like weird terminology for vapor. What this refers to is actually superheated vapor. All that means, as you can see from the TV plot, is that now it's a vapor with a temperature higher than the temperature we had under the vapor dome, and that's fine. So for a constant pressure process, this is very typical behavior for the TV plot. We've increased the temperature, the curve kind of goes up and to the right, away from the vapor dome, to whatever point we want beyond that. In the PT plot, we continue to the right. Remember, it has to be a horizontal line because we've maintained constant pressure this entire time. So we're somewhere over there in the vapor region now. We've transitioned from a liquid to a vapor. Finally, in the PV plot, you can see that we just, again, have to move horizontally. We go to the right of the vapor dome, and that's all that happens in the PV plot. Our system is now 100% vapor, meaning that there's absolutely no liquid left in the system. These are characteristic curves. Now you can imagine that they would change a little bit depending on the exact value of the constant pressure you pick, and certainly depending upon the substance, but generally speaking, for a constant pressure process, you have to see horizontal lines on the PT and PV plots. That's true regardless. On the TV plot, generally speaking, if you are crossing the vapor dome, you'll have the very steep slope on the left, you'll have the horizontal behavior in the vapor dome, and then something that has a shallower slope over on the right as you get into a superheated vapor. Being able to sketch out these characteristic behaviors on TV, PV, and PT plots will be tremendously useful when we start having to quantitatively determine states in an evolving system like this.